Good morning, good afternoon, and good evening. Welcome to the fifth episode of GroundBreakers Transforming Geotech. And today I'm joined by Andres, the technical director at Luna Optasense, who is a leader in the field of fiber optic monitoring, not only in civil engineering, but in many other applications, as you will hear today. The purpose of today's podcast is to really talk about this technology that's growing in different industries and to see how it can help civil engineers, construction companies, contractors, consultants, and geotech enthusiasts really understand how they can use this in their day to day projects, but also how they can add more impact to their lives and to the safety of the environment around their projects using this technology. Andres, welcome to the show. It's a pleasure to have you today. And let's begin by talking about a bit on how fiber optics is coming into our civil engineering industry. And maybe you can bridge that with your experience in different industries as well.
No, perfect. And thanks for the invitation, Ridvik. Very excited to be here. Uh, and certainly fiber optic sensing, it's fairly a new field, but we're finding more and more applications every day. As we all know, we live in this planet, we are surrounded by fiber optic cables to transmit data. But now with this technology, essentially, we can convert each one of those fibers into a sensor that can detect changes in temperature, in vibration, in strain. So this really opens the world of possibilities of the things that we can do with these technologies. So in civil engineering specifically, we're starting to use this. Certainly the geotechnical side of things, it's one of the areas where historically we have used these sensors as a seismic tool to look at ground movement, to look at seismic waves, to look at the effects of earthquakes. And of course, with that, as we start to instrument things like dams, things like different bridges with these fiber optic cables, all of a sudden we can monitor very different processes in our infrastructure. And really the intention is that we can not only monitor what is happening, but ideally provide a technology that enable us to understand our engineering systems, to understand nature, and understand the impact of our engineering systems on nature. So that's the whole goal of these things. Take advantage of existing cables and really turn them into sensors that can provide much more value to society.
Yeah, and I think the most interesting part is that they're already existing cables, and a lot of infrastructure has these cables, especially tunnels and bridges for their communication. So you're really turning an existing infrastructure using an analyzer into a sensor. So my next question to you is, what are the key differences and benefits of using fiber optics versus traditional methods? But also, how can they both complement each other in a infrastructure project?
Yeah, of course, this technology is going hand in hand with existing sensors. Again, we in civil engineering, we have been deploying all types of sensors for a long time, anything from displacement meters, tilt meters, piezometers, pressure sensors, all types of tools. But what fiber brings to the table is essentially a device that cable is very malleable. Again, it's the same cable that we use in our telephone lines. So you basically can deploy it in many different locations, many different configurations. And the beauty of these fiber optic sensors is that each point along those fibers becomes a sensor. Traditionally, a piezometer or an accelerometer is going to be basically a single point. So if you put many of these, you're going to have an array. But fiber optic sensing, distributed fiber optic sensing, will basically provide you thousands of measurements at once. So it really allows you to illuminate our infrastructure, to illuminate what is happening around our infrastructure in multiple dimensions, because we're basically tracking processes very rapidly in time, with a very, very fine spatial resolution, with very, very high sensitivity. So this really allows us to investigate and really understand the physical processes in a way that really has never been done in the past. So it's a very exciting technology.
Yeah, and I think because it's never been done in the past, now with high spatial resolution, with continuous monitoring, not single point monitoring, you really have that distributed sensing and you have the traditional sensing to complement different parameters. So together, it's a very, very, very beneficial tool for engineers, for asset owners who are concerned about the safety, because they get one more way to measure something to give more confidence, especially in critical projects.
Yeah,
So,
yeah, yeah. And for example, just to sorry to
yeah,
interrupt
go
you
ahead,
there,
go
but
ahead, go ahead.
certainly in let's say for example things like dams, where let's say you may have some point sensors at specific locations along dams. Now all of a sudden with cables, uh, I mentioned that one of the physical properties that we can measure is strain. So let's say if for some reason you start to have the development of a fracture or a crack along the wall of a dam, depending how we have these cables installed, we can actually track the development of those things with incredible detail, and we basically can pinpoint to the centimeter or to the millimeter, depending on the instrument that we're using, where the failure points are. So really enables us to really monitor our infrastructure much more effectively.
Yes, and I think that's really effective, especially with softwares coming up now, like what you guys have, what Procure has, as in Procure being the integrating software. You can really look at alerts, you can really warn people, and you can really like see where the issues are and take corrective action at the right time, which is, I think, something really important. And one thing interesting you said was that you can also show people the development of a crack using fiber optics, where you would normally put a traditional crack meter. And I think it's something similar that people are talking about with INSAR and satellite monitoring. So it's like distributed continuous from space, and then you have distributed continuous on surface and subsurface. So I think people are really, really moving on to different technologies and bringing it into our industry for the benefit of our community. So my next topic would be, we've been talking about fiber optics. You mentioned distributed fiber optics, but can you explain in very brief analogies the different types of fiber optic sensors and why someone would use a particular type, just to bring more clarity to our audience?
Yeah, yeah. So the way this fiber optic sensing works, essentially the same cable. Nothing exciting about the cable itself. But what we do is essentially at the end of this fiber optic cable, we're going to connect this instrument. Usually we call them interrogator units. And these units, essentially what they're doing is they're going to be sending light pulses along those fibers. And whenever there's a disturbance along those cables, along those fibers, it's going to change the character of the light. So that same instrument that is sending the light is also going to be receiving the light. And those disturbances really can be a temperature or a strain or acoustics, depending on the type of light pulses, depending on the shape, on the type of the light that we're essentially interrogating. So it's a passive sensor. Again, the beauty of it is that really you just connect it to a fiber, and you can potentially interrogate 100, 200 kilometers of fiber in one go and really look at disturbances each meter along the way. So, and again, we can detect these different features. And really, I think that the exciting thing now that we have this incredible computing power, and we have machine learning, we have artificial intelligence, we do generate a lot of data, and these tools are very sensitive to all types of things. For example, in submarine cables, we can detect motion of the currents, we can detect whales singing, we can detect earthquakes, we can detect the depth at which these cables are located, temperature fluctuations. So a very wide range of signals, but with the computers that we have nowadays, with the algorithms that we have, we can apply all of this intelligence to extract the signals out of all of these measurements to really get actionable diagnostics. Maybe there's someone who's interested on looking at cable integrity for intrusion, or maybe there's someone who's interested on using that same cable along a pipeline to detect for leak detection or for any operational issues on a pipeline. So it is the same tools. It's just how we use them to separate the signals of interest.
Yep, and I think it's really cool that it's like the same technology that they're using for different applications, from pipeline leaks to even listening to whale sing. And the interrogator actually take an existing technology and make it powerful. And something you mentioned was the current computing power, machine learning, artificial intelligence coming in. And I think with data becoming very critical, and one thing that people really were lacking back in the day probably was understanding the multiple types of data on their project. And today we have the resources for people to actually understand that data beyond graphs, beyond just a table, beyond just an Excel file. So I think that's really, really been a game changer. And as we progress in the decade with more computing power being generated, with different types of machine learning algorithms being developed, generative AI may be coming into construction. I'm not sure about that yet. So you really have that ability to give the people what they really want in any field, whether it's construction, pipeline monitoring, etc. So let's talk about a challenging or a project where you learned a lot based on your experience. Any that you can talk about? Like, what was one project that was a wow moment for you?
Yeah, so there's many projects. Again, right now we I have been fortunate to work in a company where we have broken a lot of ground and very different new applications. But one that it's has been very powerful, I think, particularly in recent years, for as we start to monitor tailings dams, as we start to monitor more geotechnical aspects, is perhaps ground deformation. So historically, let's say on the pipeline side of things or in the power cable monitoring side of things, traditionally we look for integrity. We want to make sure that there's no leaks on the pipelines or there's no power overloads in our power cables with a temperature increase. But while monitoring a pipeline a couple of years ago, we were looking for basically for signals associated to leaks. Very easy. Sometimes it's someone approaching a pipe, want to do something harmful to them. So those are easy. But this time there was this system in the middle of nowhere, and there was a portion of this buried pipeline that had a very strange signal. And we were like, well, what is this? It doesn't look like it's a leak. None of the diagnostics is indicative of a leak. But it was a very clear strain response. So by processing the DAS data, this was using distributed acoustic sensing, we basically looked at the very, very low frequency component to it, where we traditionally now we understand that we're getting more of the strain, pure strain, basically just stretching and compressing the fiber in 3 dimensions. And what we found out was that in the middle of this pipeline, in the middle of an agricultural field, there was actually a sinkhole that formed during the operation of this pipeline, and the pipeline didn't burst or anything, but it showed us that we can use these tools to track very, very subtle ground deformation. And this becomes important because at the end of the day, we want this infrastructure to last a long time. In this specific case, we realized, well, guys, there is a sinkhole, so the pipeline is still sound, but maybe you may need to reinforce it or take some action to make sure that infrastructure continues to work. And I think that's part of the power of real-time monitoring. That forensics is nice, it's good to have data that understands why certain things failed, but the power of monitoring, the reason why we're instrumenting so many things with fiber, is that in real time we can detect changes. We can detect if there's a problem or there's a formation of a problem, so we can take proactive action and hopefully prevent failure to occur. That's the beauty, and I think that's perhaps the mindset that I hope we can start to change. Be more in the framework of prevention by monitoring instead of trying to figure out what went wrong. We have the technology to monitor it. Let's use it.
Yep, I agree with you. And I think real-time monitoring really gives people that opportunity to uh, build awareness about their infrastructure and the construction side and know what's happening before something happens and take actionable insights with your data that you're getting through real-time monitoring. And fiber optics is another big, big key in the package that people are probably looking for beyond just traditional manual readings going to a site. And I think even with data logging capabilities now coming up with IoT, with processing on your interrogators, it's really that one-time setup and then probably some maintenance, not even every day, a couple of months, and just ensuring that your data is safe and project is safe with the data that's coming in. So I think technology is
Yep.
really, really helping us grow. And I think that's been one thing that has been at the pillars of many industries throughout time. So my next question would be, we talked about a challenging project in a tailing dam currently, whether it's a sinkhole. But in what other fields outside of civil engineering have you had some interesting learnings during your time?
Yeah, so I think one of the again, there's certainly seismology, for example. My background is seismology, and certainly earthquakes and volcanoes are close to my heart. And one area that has been very exciting has been to essentially take advantage of, again, fibers that we have along highways or along power cables, and turn them into seismic sensors. So now we are increasingly using these for early warning systems when we in places where we have large earthquakes. I'm based in California, so we have that problem here, and it has been very exciting to see how seismology has taken this technology and really taken advantage of available infrastructure to have many more sensors, have more coverage in areas where we traditionally don't have sensors. Another area where we have done a lot of work has been certainly monitoring wells. Again, right now we can monitor water wells, geothermal wells, oil and gas wells with fiber optic sensors. And something exciting is that we can actually understand the dynamics of wells and see how the fluids are propagating, the interaction between the fluids in the wellbore and the environment. And this has really become very important because we don't want problems with, let's say, oil and gas wells. We don't want these things to leak. We don't want these things to blow up. And we have learned that basically these fiber optic sensors allow us to detect very, very subtle changes in the fluid dynamics, in the well dynamics, in the pressure and temperature regime that can diagnose if there's a problem with the well before it escalates, you know.
Yeah.
So more and more companies are really taking advantage of this permanent monitoring to ensure safe operations. You know, at the end of the day, we want to make sure that our engineering systems, certainly they're designed to certain specifications, but by turning monitoring into a real-time tool, we really can ensure their safety and their integrity for the duration of their life. You know, so that is a very powerful asset of this type of technology, that you basically can install your fiber from the very beginning of your project and monitor cement curing, monitor vibrations associated with the construction, monitor strain changes once that infrastructure is under utilization, whether it is close to vehicles or under strain or temperature conditions that could put the system at a potential fault. So we can really track all of these physical processes. So it's a very exciting tool.
That's really cool. So you can actually take an analogy with human beings that like since like the birth of the child, you can monitor it until the infrastructure ages, and with time, infrastructure does age and needs maintenance. And fiber optic, at least distributed, are like the nerves of the human body that throughout the infrastructure's body, and then you have point sensors wherever you require,
Yeah,
and you do surveying
yeah,
where
and that's
you require it.
yeah, and you mentioned earlier the difference between these fiber optic cables and conventional point sensors, and the point sensors are very powerful. Believe me, we integrate into point sensors all the time. But cable, again, glass at the end of the day is silica that has been uh, can withstand very high temperatures, pressures, can really withstand the test of time. We have cables inside of wells that have been operating for 30 years under very high pressure and temperature conditions. So we really can, the glass itself can take a lot of pressure and strain. So it really can last a very long time.
Yeah, and I think the materials there, that was something new I just learned. That's very interesting. And I feel like if your cables are that durable, then the people also get more of faith that they're not just installing it for a year or two, but 30 years, 40 years and beyond. And you can also scale it up for a couple of 100 kilometers as well, if required. So
Yeah, yeah.
yes, I think the whole package coming together is a very, very useful package for people to really monitor the safety of the assets in the way we take care of our own healthcare in that matter. So my next question would be, what got you into fiber optics? You said you were interested in seismology, but what made you get into this technology?
Yeah, so actually I was working on seismic monitoring with conventional sensors. And when we started to work on these tools, we were like, well, we can actually detect um, basically seismic vibrations with these fiber optic sensing machines. And it really opened the possibilities because it started from a borehole seismic surveillance where it's usually difficult to install this type of sensors inside of hot and high pressure environments. And all of a sudden we have a device that really you could put it anywhere, so and on top of that, you have a tool that basically allows you to have such high receiver density. All of a sudden, not only do you have a seismometer close to the San Andreas Fault, but I have thousands of seismometers along 100 or 200 kilometers of road next to the San Andreas Fault. So it allows you to really investigate many different types of physics associated to physical phenomena. So really the adoption of these tools has been very rapid. We developed this technology in Optasense around 2007. Those were the first case studies for seismic monitoring, and it really now it has taken off. And right now we have earthquake networks monitoring with fiber optic 24/7, with submarine cables, with land cables, buildings, bridges, really, and even things that are not as sexy, like there's pipelines that are carrying water, but there's also sewage lines where we that are along underground conduits in cities that we are tracking signals associated to whatever is happening in all of those conduits. So smart city applications, not just from a geohazards point of view, but from a utilities management, monitoring our power cables, monitoring our roads. It's something that it's now routine, and it's basically commercial products that are available. So.
Yeah, and I think that last part about smart cities and monitoring not just geohazards but utilities really gives
Mm.
this another edge that people might not know about, where you can really place a cable or use an existing cable, add an interrogate, and just have your data coming to you every day. And it's a once in a lifetime investment in terms of going to site and setting it up. Once it's set up, you're not going to go underground and fix the cable unless something really,
Yeah.
really rare happens. So I think it's a very interesting tool. And interestingly, it went from testing and then you found a new technology that could really help you do what you love. And ever since then, it's kicked off from beyond seismology to pipelines to wells to even now bridges, dams, and I think it's getting to monitor a lot of the earth if you think about it, because most
Yeah,
of the
mines,
to this fiber
mines, for
mines as
example,
well.
mining. Now that we are starting to be so reliant on critical minerals for our batteries and things like that, so mining all of a sudden has taken a very large prominent role, and that's another area where we're monitoring a lot of underground and open pit operations to look at strain, to look at temperature, make sure that the conveyors are working properly, make sure that the ventilation systems are working properly inside of our underground operations. So really, it's not just a science and engineering. There's a very big aspect of safety that fiber optic provides to manage different types of assets.
Yep, and I think the safety part of it is super key, especially for concerned asset owners. And I think engineers also like having a easier technology to use, which fiber optics really gives them. So, my last topic would be for people interested in fiber optics, for people interested in the safety of assets, or even smart city applications for utilities. What would be something you would give to upcoming students, young engineers in the field as an advice on how they can go ahead and really get involved in this technology?
Yeah, so that's a great question, Ludwig, and I would say that again, historically, again, this type of sensing, maybe some of the fundamental physics fell within electrical engineering, maybe computer science as far as the data analysis goes. So what I would encourage civil engineers or geotechnical engineers is that traditionally don't have a strong signal processing or data science to really get into those areas, be open-minded about exploring different technologies. Yeah, we get very comfortable with our displacement meters or with our pressure sensors, but there's other tools that can give you the same measurements, maybe in an indirect way, but we need to be able to understand the physics of that. So yeah, I would say signal processing for new engineers is something that I strongly recommend. Fourier analysis, of course, data science with all of the aspects of machine learning, because again, we do need more and more algorithms to go through all of this data. If I would say one of the criticisms of this technology is that we generate a lot of information. So we're constantly looking to tools that allow us to digest this information, to have an actionable diagnostic that tells you you have a crack, you have a leak, you have an earthquake approaching, or waves from an earthquake, whatever it may be, you know. So again, all of those diagnostics, we need to really put them together. And again, that's a combination of physics, signal analysis, and increasingly, again, ML and AI.
Yep, I think that was great advice, and the signal processing part is something very important along with the machine learning because
Mm.
predictive is becoming a very big trend in the future, and people are now really trying to figure out how can we predict and be warned early. So, Andres,
Yes.
today we talked a lot about fiber optics, the different types of fiber optics. One of the key parts that it really brings awareness and early warning systems for the safety of our infrastructures, how fiber optics is being used in multiple applications, not just construction, not just civil engineering, but even utility monitoring, and how today with the computing power, with the technologies, the amount of data we get, we can really understand it and process it. And I think it's a tool for the future for sure. And as we're trying to, as our groundbreakers transforming geotech, we're talking about technologies that can transform our industry. This is for sure one that's really, really going to have an impact in the future in the way we monitor our assets, in the way we have safety in smart cities, and in the way we use day-to-day technologies like fiber optic cables to really have actionable insights. So
That's right.
so
Mhm.
much. It was a pleasure talking to you and hope to see you on another episode in the future.
Same here. Thanks for the invitation, Riddick. We'll be in touch.
Thank you.